let's do the thing. So first, I want to, it's the link in the chat. And so go ahead and click on that link if you haven't seen this already. It shouldn't matter if you're on your phone or on your desktop or whatever device. Hopefully what you're seeing right now is one of our samples. So let me start by introducing myself. I'm Mike Acton. I run the DOTS group in Burbank, California. And one of the things that I've been talking about for a long time is something that's now called data-oriented design. I thought today, I've tried, it's gone through a lot of explanation, a lot of iteration in terms of, what does it mean precisely? If we look at the where it started, I mean, it's not been, we've not been talking about it long enough for the history to be super vague. We know how it started, and I think that we look at, really it was the PS3 when that came out, that really made everything that was coming soon and all the potential problems that we were thinking might come, definitely were there. Were very real, very immediate, and you just simply couldn't get things done without considering the ramifications of your data design and the architecture of the machine. You couldn't ignore the architecture of the machine and expect results that made any sense at all. And so it was around then that it was, okay, well, there's lots of best practices around this. Like we handle this, like we do this. So, this was a sort of process of wrapping up those best practices that existed over and were built up over decades of work. And then that sort of evolved into a more discrete set of things and a clear description. But really what it comes down to is some set of principles. It's much more of an engineering approach and mindset and strategy than it is a particular set of steps or certainly not a particular technology. And in fact, if you look at sort of we generally contrast it with the object-oriented programming. But if you look at object-oriented programming as sort of a modeling approach, you can, to a degree, you can think of data-oriented as one somewhat orthogonal to the question of modeling, because you model in a variety of ways, but sort of also an anti-modeling approach and a much more like actual, like get the actual data approach. Hopefully that gives you a little bit of background. While here's a link to the rest of the tiny samples. Feel free to check them out. Sorry? Okay. So if you feel free to check them out. So just as a broad overview, you can think of DOTS is a couple of things. One, I'm going to spend most of my time today talking about data-oriented broadly, but I want to just let you know what DOTS is. You can think of it as a collection of things, and it starts with it really starts with what we're calling the kernel, which is just the most basic set of things. Like if you wanted to provide a sandbox in which you were building a feature, what would that sandbox look like? Sort of the minimum set of runtime things. And practically speaking, that's collections, some ability to manage memory manually. And it's a job system, and it's ECS, which is really just a ECS. There's lots of lots of analogies for ECS. So some people, it's helpful to think of it as an in-memory database. It's a set of tables. But it's what it is it's a good default. It's a good default for memory storage, and it's also a way of it's a specific protocol or some specific way of defining a protocol, such that systems know how to interconnect to each other. And you can say, system A, I want stuff like this. System B can say, I have stuff like this, and there is a way for them to communicate that. So that's really the kernel, and then it's the pieces that you put on top of that, and you define through those ECS data protocols. So in what the samples that you're seeing here, these are just standalone examples that were just built basically on top of that kernel. So a renderer was put in place that spoke a renderer protocol, data protocol, which is, in the sense, is just some set of components. A small little audio protocol. This is, basically a component that says play here, and some animation protocols and so forth. This is so the collection of those systems that implement those sort of tiny protocols is called Tiny in our case, and it's intended to be as small as possible. And we can compile it for whatever target. In this case, it's the web. But is easily compiled for Android. So if you look at that as sort of that standalone runtime, the standalone engine, which you see running here, there's also the possibility of, say, putting, like, what if you plug that into some other environment? So you took that engine and, say, you put it into Unity, and you just sort of during the Unity update loop, you just took a chunk of that time. You just said, okay, in here we're going to run this other engine, basically right here in the middle of the loop. So what would happen, and what would happen is what we call a hybrid mode. And so when we talk about hybrid and dots in Unity engine, that's what we actually mean, is that kernel and those whatever the systems are running inside of the Unity loop. And we have we have some special sort of runtime systems and feature sets that run in that hybrid specific loop. So our hybrid renderer, for instance, is specifically designed only to run in that Unity plugin scenario. Because you can define things in such a way that the environment in which it's plugged in, right? Dots animation, for instance, is intended to be run in either scenario, in any scenario. Certainly anything that can run in the standalone scenario can run inside the hybrid scenario. And so that's really it. Then the only other part of the piece when we're talking about plugging into Unity itself is how do I get the data in there, right? And so when you plugged it into Unity, it turns out, of course, you've also plugged it into the editor by default, because the editor is Unity. So we've added something called the conversion pipeline, which should be no stranger to anyone conceptually. It basically, conceptually, is just, I have some data in the editor, and I want to bake it into something that actually is usable at runtime. That's really it. And so in this specific case, what we mean by that is take anything I have in the tool and convert it to, and bake it down into these data protocols, bake it down into component structure, binary, straightforward, loadable, and mappable protocol. And so that's really all the conversion pipeline is that here's the scene, or here's the sub scene, or here's the prefab. Turn this into a file format that matches the runtime binary protocol. And so that runs and updates when things change and spits out that binary file, and you can load that and stream that at runtime. It's fairly straightforward. So that's really sort of the introduction to both the standalone, which is as by way of example, the standalone is tiny, what you're seeing here, and the hybrid Unity interface, which you can see just by running whatever version of Unity you're running now. Now where I want to get to is to sort of take a step back and talk about data-oriented design more generally, and sort of why what we're doing is a different approach. It's not just different tech, although it is. It's a different sort of mindset on the problem, and then sort of what we're trying to nudge toward is a different engineering approach. And I thought I'd take this opportunity to try out and I appreciate y'all being my guinea pigs here, to try out a sort of newer description on the methodology, on how we approach problem solving, and see how it sticks. So with that being said, let me start that out. So some of you may recognize this from an article, from a science article recently, and if not, it's not a problem. So there was a study done, and it's a simple one, which is given this set of actual Legos like this, or not Legos, but bricks. Well, I don't know why that pops there. What do most people do when asked what they need? Well, what do most people say when asked what they need to fix this wobbling bridge? And under pressure. So an important part here is under pressure. So this is all timed. In the case of this study, you have 60 seconds or 30 seconds or whatever it was. Under pressure, almost everyone defaults to an additive strategy, which is I'm missing a brick. I need another brick, right? I need to add something to the problem in order to solve the problem, and I'm missing the thing that I need to add. Like I need to get something from the outside. Like I need something. And very few people approach the problem from a subtractive strategy. So, I need another brick is the default for most people. Under pressure. And removing a brick is really not the default for most people under pressure. And this is really, really interesting, because we find this to be, in fact, true across the board. And if you think about under pressure, right, okay, so I'm reading the chat. There's no vehicles on a Lego bridge. It's not removed. This bridge is not representative of a real bridge. This is actually just some bricks. And so the question is, how do you make it flat? So it's not intended or was even presented as a representation of some other sort of, real world bridge. Now, it's entirely possible. So I think that there's probably stuff to unpack here, because it's entirely possible that quite a lot of people do implicitly do what you just did, which is use it as a, add something to the problem that is just not there. and they look at it and okay, this must immediately think this is a representative of a real bridge, and that's the problem that they're trying to solve, is how would I solve this for a real bridge? You've just added something to the problem that definitely wasn't there. No one said that. No one even suggested that that was true, and yet you're solving that problem, and you're doing it automatically. Right, I'm sort of automatically jumping to that. I'm automatically bringing that in, and I think that's an interesting example of what we're talking about. And so, if we come back to data oriented in particular, what data oriented is at its heart is a subtractive engineering strategy. The point is to help developer, help whoever, focus on what you have. It's about sort of deeply focusing on pieces that you have and understanding them well. And in quite a lot of real life scenarios, you sort of already have everything you need. You just need to understand it better. And you need to get pieces that are sort of the pieces that are in your way out of the way. And often those pieces are mental. I've built in some set of presumptions in here that aren't true. They may be technical in terms of code or data that you've written, that I've built this abstraction that adds something to the problem that is actually not in the problem itself. Like I've created another problem by adding this thing in here. I've built a new idea into the system, into the machine. And that idea adds its own set of problems. And if I just got rid of it, I would in fact find the whole thing much simpler. So that's really what it is about understanding what it is that you have, what it is that you need to do, and get everything else out of the way, sort of sweep things clean. And so if we look at it as an engineering strategy, there's really four key elements to that strategy. So one is focus only on the data you need for the task at hand. You're trying to do something. What do I need? What are the inputs that I need to solve this problem? And what are the outputs that I need to solve this problem? And that's it. Focus only on that. And then understand the pieces that you have available to you. So this is about generally two things. One is the analysis of the data itself. This is the frequency of occurrence, and these are surprising things. And it usually comes down to sort of what's surprising and not surprising from an information point of view. It's not surprising that, say, 99% of this value is 0 or 1. So I can in fact use that fact to make some decisions. Occasionally maybe it's 0.01% of the time, maybe it's some third value, right? So I don't actually need the common. I don't need the common path to deal with that, right? I know that coming in. So I understand that, right? So it's about understanding that the data that you actually have, and not pretending that you can't, because a significant percentage of the time you actually can understand either likely or common. And the things that you absolutely cannot know still have a finite range, and so you can work with that. 3 is understanding the costs that you're already spending. So you can't do this without understanding the platform on which you're running. How much does it cost? And this is also from a development cost point of view. But how much does this cost to transform this piece of data? How much does it cost for me to do X on this platform? And if you can't reason about the cost of a thing, you can't reason about the solution at all. Like, it's pointless. You're just guessing. Or you're building your solution against some sort of abstract model in your mind of a device, and it's implicitly, when somebody does that, it's implicitly probably something very similar to the workstation that they're actually sitting at, because they've sort of mentally modeled that workstation, and that's not appropriate for a lot of devices. And then finally, the strategy is, once you have done that, is just to sort of organize your pieces, get organized. It's an organizational strategy for data and code for what you do as a programmer. And so organize them so you get more value out of them. That's it. That's the whole strategy. It's and it's hard to not, it's not complicated, and it's intentionally not complicated. It's just about understanding and organizing. So I wanted to sort of step through each one of these and see if I could explain it a little bit better. So the first one, focusing on the data you need to accomplish the task at hand. Conceptually, less things is powerful. And remember, this is all about under pressure. Development is pressure. Work is pressure. Making a thing for a user is pressure. That the pressure in the scenario that we started with this study was, you have 60 seconds to solve this puzzle that actually has no meaning in your life. Like, that's enough pressure to trigger an additive strategy. Your actual job, the thing that you're doing, is considerably more pressure than that under any conditions. So what we're always talking about is under pressure, and that influences your choices. That under pressure is part of why data oriented is the way it is. So if we look at the scenario where I'm under pressure to turn on a light, simple. So it's dark, I need to turn on light, and I have 5 seconds. This one is not what I want. I am under pressure. I do not want this one. I want this one. Because under pressure, what I need is one bit of data input. I need to know which direction is on, and one bit of data output. I need to flip the switch on in that direction. And there's way too much, there's way too much input happening here. Maybe I can model this as one bit of data input, right? I can sort of pre-filter it in my brain after I've used it a million times, right? And at some point, it's basically muscle memory and automatic, and it's basically just that one bit. But under this condition of sort of under pressure, where I'm just presented one of these two things, then there's no chance. I have not done that. So it's considerably more than that one bit of input. But even if we just look at this switch, which is clearly better under this condition, and it's easily testable, like we could put people in a room and just say, turn it off and time them. Even this example, which we all know, it fails to provide that one bit of input well. Like this only works because we mentally modeled it after I've using it so long, in the same way that if we practice the other one, we could mentally model that one. It relies on you already knowing which way is on. You already know that. Or you look very, very, very closely at the switch and you see that, so you have to look really closely and you can see that it's on, which you need to do with a light. That's off. So like this is some really terrible UX in that regard. So what I actually need in this space is much more like this, right? I need it to be, say which way is on. I need that one bit of input. And so this is really about, this comes back to the principle of focusing only on the data that I need. What's that? What do I actually need? I need that one bit. And that tells me, this is the bit that I need. And it told me, in fact, when I was looking at that switch, it told me that the switch actually didn't provide me the one bit of input that I needed. It helped me to analyze the situation. And so just being explicit about what data that I need helps guide the strategy, engineering strategy, right? Helps guide the process. And focusing on what data that I'm giving you. Like, here's the output explicitly. This is all about being as explicit as possible. So data orientation is not about creating more abstractions or more details to understand. It's about subtracting anything that's not strictly necessary to solve the problem at hand. It's like, I want to know what I need. Make it simple for me. What are you going to give me, and what I need to give you? That's what we need to simplify it to. We want to know, in order to solve this well, we want to know who is trying to solve a problem. Like, who is the person that's using this, right, from your point of view as a programmer. And you have to think about what skills they have, what do they already know, what's implicit knowledge. You have to think about what outcome that they're trying to achieve. Like, and this is all, you can think of this as very much tied to usability. Like, they seem like usability questions. And the fact of the matter is that they are intimately tied. These are not separable questions. You can't design a system of any kind. You can't engineer a system of any kind without considering the use of that system. And you can't simplify a system to its basic core without understanding the basic use of that system. So you need to know, what matters to them. What are they trying to achieve? What exactly is the output they need, which is what you're providing. Even what's the day-to-day environment like? This gets back to the question of pressure, because the more under pressure that they are in that environment, the less likely they're going to be able to reason about more complicated output, or it's going to take them longer to do. And the more likely it is that they're also going to add things to the solution that you're giving them, or to the input data that you're giving them. So you have to consider what conditions that they work under. Now, as a game engine, now realizing that other people, other industries use Unity, but as a game engine, a lot of our users are game developers. And a lot of the time, those game developers are notoriously under deep pressure, maybe crunching, certainly, probably worried about a bunch of things. Probably things are in a state of chaos, but there's a lot of pressure. And so that affects their decision-making, that affects what they do with the solution. That's constant. And so that's part of the consideration in terms of your design, in terms of your engineering strategy. If you can't just simply assume that everything that that there will be some rational, well thought out, long process of, okay, here's the API that they're providing, here's what I'm trying to accomplish, and they're going to sort of sit down with a piece of paper and model those two things out, and they're going to have some meetings about it, and they're going to get some professional people together to do a professional job of sort of outlining that, and being really rational about it. You can't assume that happens, and I would say that the chances of that happening are almost zero across the board. It's usually somebody sort of eyeballs the thing and hacks away at it, and maybe if they're stuck, they take a glance at some documentation, and then they watch a YouTube video about it, and then they try something else, and it's, like, generally speaking, not a well thought out process, and then they start adding things to it. Maybe I can make it. Maybe I can, make an abstraction around this, like, which is often the immediate response from especially programmers. And so they start adding more complicated things on top. So understanding their environment matters is the point. And so data design in general is sort of deceptively a hard part of the problem. What we need to define as part of the process, and why we need design as part of our process, is we need to know what exactly are the minimum amount of input bits required, what's the minimum set of data required in order for the user to solve the problem at hand. And we need to get everything else out of the way. Like, what's this minimum set of data that they need? And what's the minimum amount of output data that they need from us in order to solve the problem at hand? Then we need to get everything else out of the way. At a high level, you can sort of look at this like even in the editor, right? From the user experience at that level, sort of the data-oriented approach applies at that level, which is I'm trying to say, I mean, at the highest level, I want to make a match 3. Like I'm opening Unity. It's one of the most common things that somebody's going to want to do with you. I want to make a match 3. And I open Unity. Like if I look at what's the input data that I'm seeing, what's coming in right now, the vast majority of this stuff that's being now thrown at me is not something I need in order to make a match 3, right? And all it's doing is complicating the situation for me. All it's doing is it's presenting that complicated switch interface when what I need is a simpler switch, right? I just need the input that I need for the scenario in which I find myself. And so data oriented is really about defining that scenario, defining those inputs under those conditions, and really knowing it. Now, that's not to say that you can't have a fallback. We don't know. Like there's some finite set of things we don't know, so therefore you fall back into okay, here's just a general pile. Here's just a really generic thing, and we do that with, say, memory management. It applies there. So you can have very, under conditions in which you know the memory that you're dealing with. Maybe you have some very specific kind of memory layouts. Maybe you have some very specific kind of containers that manage memory. And it's all very statically managed. Maybe you have bucketed allocators and different kinds of allocation strategies there. So that you don't have to go through any kind of like heap allocation at runtime. Like, it's very common, right, to have essentially 0 heap allocation during the course of a frame in a game. But then maybe something comes by where you're, some piece of data or some system which you didn't really anticipate. Maybe it's a third-party plugin, or maybe it's some middleware or something. And so you have to, under those conditions, you sort of fall back to malloc, right? And say, here's heap. Like I don't know enough about this, and so it's a fallback scenario. And so from a design point of view, when you're designing a system of any kind, you can still have that. You can have okay, well, we don't know, so here's the fallback, and I can gather information from the fallback, right? And so there's a place for that. And so it usually starts with the question of what's most common when we solve any problem. What's the most common thing? That's the question that we most commonly ask as part of the strategy. What's the most common piece of data that we see here? What's the most common task that a user is likely to do? That drives everything, really, because what you're basically doing is stack ranking by frequency of occurrence, and then just working from the top down. And the reason why you do that is basically it's a progressive approximation of the right answer. It's the sort of and from an image compression point of view, right? That should sound familiar, because that's precisely what you're just doing on a larger scale. And you're doing that as an engineering strategy. And so in order to understand what's most common, you need to, again, understand the basic data that's going in and out of the system. So information, the minimum information that we need to know, the most common time sinks in their loop, what errors are most commonly made, because those are going to change what's most common. Errors are going to change what's most common. So because that will change behavior. So what mistakes do people most commonly make? And they usually make it because most often people make mistakes, especially if we look at the light, again, to go back to the light switch analogy, people make mistakes because they don't know what to do with the data that they have. They're presented with too much information. They're presented with data that they can't reason about under the conditions. And if the default is the only reasonable answer to the question at hand, you should not even have to see the default. And that's just as true at runtime as it is in the UI and the tool, if there's only one answer to the question, I shouldn't have to answer it. Like as a general principle, that should be true. And when you have a fixed general purpose, general AI API, for instance, or a fixed general purpose UI, you can't solve a problem like that. And so this is somewhat antithetical to those kinds of approaches. So, asking part of this is asking what's most challenging for users to provide good data. So, this is what I would need from the user, this input, whether that's from a programmer, I need you to provide like the rotation on this, and if we say it's a rotation component, right? And we're talking about programmers, and say I asked this question: what's the most challenging for programmers to provide? Maybe it's a quaternion rotation component stored in quaternions, right? Or stored as a quaternion. And I can say, if I look across what's most common for the users that I'm looking at, and maybe the users that I'm looking at in this case are the most common gameplay programmers, and in that scenario, we would say I'm looking at basically self-taught gameplay programmers who learned online in the last, say, 3 to 5 years. And that's not all of our audience. And certainly we would never suggest that, you design for the lowest common denominator, but that is an audience, and that is a user that we solve for. And I guess another point would be, another data-oriented principle here is if you have a different problem, you need a different solution. And if you have a different user type and different user experience, you have a different problem. And so the solution for one set of users is entirely different. If I'm presented an expert user who has 20 years of experience building engines versus someone who learned online, by cutting and pasting gameplay code from Stack Overflow, the solutions that I present to those two users will be entirely different. And they should be, and we should support that as an engineering strategy and as an architecture. So in order to do that, we need to understand what's most challenging. So in the case, back to the case of rotation, if we look at that set of gameplay programmers I mentioned, they would struggle with provide this rotation as a quaternion. When what they think how they naturally model it is almost certainly going to be in Euler rotation. And so I need to get that input out of their head, right? And so, which is why, okay, we can provide separately provide a component that's, say, an Euler rotation component, which then we have a system that says if that exists, then I can automatically convert it into a quaternion and continue the pipeline at runtime. So to sort of go back to different interfaces for different users, that's sort of fundamental to DOTS as a stack, right? Is those data protocols are explicit and flexible. So if that component exists, if I put in that Euler rotation component, then the system which transforms that into, so you can think of it as a sort of a conversion pipeline, right? The system that transforms that into a quaternion will run because that data exists. If it doesn't exist, if there is no such component, and I just have, say, the quaternion, the quaternion component, then nothing happens. Like that conversion system doesn't run. But in fact, there's another step in the pipeline that converts both that. If that quaternion rotation and translation exists, it converts it to a 4x4 matrix, that sort of thing. That's the whole pipeline. But I could also put on top of that, an alternative to that rotation Euler rotation component. Maybe I would put on a 4x4 matrix on top of that quaternion, which I then on top of that I put a and so which I could just provide, which would be automatically inverted, or maybe now that I have the 4x4 matrix, I can provide a pivot scale and a pivot rotation component and maybe another Euler rotation component. And if all of those exist, it will use those to build the 4x4 matrix, which is basically the Maya, the sort of Maya pipeline, which will then be used to convert, which will then be used to create the quaternion and the translation if all those things exist. So the point is the interface that's presented is defined by the data protocol, and the data protocol is based on, this is what you need. Like under your conditions, what of this do you need? And that's what you can use. They just put that in, map that to your use case, map that to your skill set, map that to who you are and what you're trying to accomplish. Build your own pipe. And so that was sort of like the summary of that first principle and what I mean by it. The second one is understand the pieces that you have available to you. So our users need to need tools to help them focus on what's important to them, help remind them of what's important to them. It's unreasonable to ask a person under pressure to do that continuously without the tools. So, if you have lots of immediate concerns, and if you're a developer, you do, it's natural to get distracted and just do something that is going to cause you to shoot yourself in the foot. Part of the data-oriented strategy is to analyze the data, analyze the cases, analyze real life. And in real life, under real pressure, this is exactly what happens. People make stupid choices. And that's not because they're stupid people. That's because they're under pressure and they get distracted, or they don't reason through all the pieces that they're dealing with. Because that's not a reasonable thing to suggest that people do. People aren't like that. They don't work like that. They're going to do something which is going to cause them to hit a wall. They're going to make a choice in the moment that's going to cause them to hit a wall because they didn't anticipate it, because they didn't think about it. And so what we need is a mechanism, a practical mechanism that sort of helps you make less mistakes, right? Helps you makes it more likely statistically that you're going to focus on the things that matter to you most, that are most important to you, right? That are going to have the least bad impact. And so as a mechanism, as a technology mechanism, that's what DOTS is, right? It forces you to a degree to say you need to define your data protocol explicitly. You need to define what those conversions are explicitly. You need to declare what's readable and writable about that explicitly. And as a matter of course, you need to do that. And then if you just do that constantly and it's habitual and it's just part of the work that you do, even if it seems at first, it seems like extra, or it seems work, right? Because I didn't think about this before. Of course, it seems extra because you didn't think about it before. That doesn't mean it wasn't part of the problem before. It just means you didn't think about it. And so you shot yourself in the foot. So we're forcing you to think about this. And then over time, it doesn't seem extra, right? It's sort of built in. But it's just because we've built up that sort of muscle memory, we built up that habit, we built up that thing that you need to do, that engineering approach that you just do as part of the course of things, you're going to be statistically less likely to shoot yourself in the foot, which is sort of the point. If you look at the resources, when we talk about the pieces that you have and understand the pieces that you have in broad categories, you have two sort of things. You have the code that you've written, and we can spend all day arguing whether or not these categories are overlapping or whether or not code is really data, but let's just call it broad categories. Good enough. So you have code, you have your data, you have the available skills as a real set of resources. Like you cannot solve a problem without considering the available skills. And you have the platform, or set of finite set of platforms that you're dealing with. You need to understand, the platform that you are targeting in order to, how does that platform affect your design choices? That's the actual question that you want to ask as a user, right? And so when we say understand your platform, when I'm talking to an engine programmer, or I'm talking to a systems level programmer, I can say, RTFM, like there's a manual, read it. I can say that, like that, they know how to read the manual. They've read many of them, like they can understand the platform that way. But if we're talking about someone who is not a systems level programmer, and hasn't gone through that before, or is maybe, more of an application programmer, or a gameplay programmer, or not even a programmer at all, maybe as an artist or designer, that's not an appropriate answer. I can't say RTFM to an artist. As much as I would like them to read the manual, that's not an appropriate response. But they still need to know this answer, right? They still need to know how this platform affects my design choices, because it does. It absolutely does. There is no world in which, I'm an artist and the platform that I'm running on, the game that I'm building, it doesn't affect my work. Of course it does, right? Of course it affects how big is the texture that I can build, or how many can I have, or how how does compression work? Is it transcoded at runtime? Is it not? Do I need to do it offline? Do I need to like all of those choices affect me as an artist, and I can't even reason about what I'm doing in terms of my craft. The actual professional, I'm responsible for the quality output, right? I'm responsible ultimately as an artist for, if I'm building a texture or a model or whatever, for the thing that you see on the screen at the end of the day. I made that. I'm responsible for that. And I can't reason about the end quality, the end product, unless I know what, how that platform, where it's going to run affects my work, so that I can model it, so that I can make sure that it fits. There's no better example of this than if we go back to NTSC, right? And we look at, we look at art from those days, or, you just gonna look at game art or even television. Those designs, artistic designs would only work in NTSC, would only work because, it relied on, it took advantage of the platform. Because if you didn't know how the colors bled on those devices, if you didn't understand how it was going to look on a TV, then you couldn't practically get the result that you wanted. Or it would look like crap. And you can sort of look at any game or sprite or texture that was designed for NTSC output devices on your monitor now and see what kind of it looks like garbage, because it wasn't designed for the device that you're using, which is why we have CRT filters and all the things in order to try to make old games look halfway decent. But you have to understand this question, and so we have to be able to present this data, and we don't present this data well. Also, when we're designing a system, we need to, understand those available skills, but we need to help users understand what their skills are too. Like they don't often understand them. What can I do? What are all the skills? So if you think of it, your system, right? Whatever system you're working on, think of it in terms of what skills are there. What are the actual practical skills that someone needs in order to effectively use this system? And are there different sets of users, right? Are there people with different skill sets? Like there's a user of this system that only has these two skills, right? So imagine you're making a test, a user test. And this is not judgmental. So imagine you're making a test that says, we're going to go through and test you on these 50 things, and you know, can you do this? Can you do this? Can you do this? And so imagine how you would write such a test to prove that a user could do those things. You know, and it could be as simple as you know, we're providing a C++ API. Therefore, one of the skills required in order to do this is you can use C++ and you can manage to compile a third-party plugin, and you know, those are sort of set of skills. So what are all the skills needed in order to use the system? And if there are different sets, like different user sets and different skill sets, then you should be able to tell that to the user. These are the skills that you need. And if you have, you know, and user A type needs these skills, user B type needs these skills. And if your user B type needs this is your interface. These are the things that you care about. This is the things that you need, user A type. So they should be able to self-select into that group because they know whether or not they have those skills, and they can start to reason about their own skills. We don't do that well. You know, and I don't mean we Unity, I mean we, the world, we, the industry. This is not something that we do well, is you know, let users know what skills do you need in order to be successful using this. You know, and that's one of the core principles of data-oriented, is that we can start to reason about that sort of thing. So the user should understand what data that they have, and we should be able to help them do that. They should understand how it got there. You know, I have this, you know, I have this structure at runtime. How did it get here? Who put it here? Why did they put it here? You know, what were they intending by putting it here? That's context that you have to know in order to reason about what you're going to do with it. You know, what's the impact of changing it, right? If I approximate this, what's the impact of that? What are the constraints? You know, not knowing the constraints is what gets in our way, right? I don't know what the constraints of this are, so I don't know whether or not I can change it, right? And so that gets in your way. You have to know those constraints, and you have to be able to articulate them. It's, you know, it's okay to approximate this to you know, in sort of an 80% error. That's okay, because it's just, you know, it's just some background gameplay code. But how would you know that if it's not explicitly written down? And then, you know, you should, as the last and least actually of all of these things, the least important of all of these things is, but you should still understand is the code. So you should understand where it is, what's intended to solve for, and reasonably predict the cost of execution. And also the platform, right? That's the design impact of the platform we're on. So looking at our time here, I am going to go really quickly to 3 and 4. So understand the cost of your already spending. You know, we need to give our users insights into the most common things that they do and how much those things cost. If we expect them to make good decisions. So when you look at whatever system you're building, you know, just ask that question. You know, are we able to give the users insights into that? Are they able to know from their side what is the most common thing that they do and how much does it cost in order to make good decisions? So doing that, building in that kind of analysis, right? Or helping users to build in that kind of analysis is an important part of the process. And then finally, right, the sort of, once we have all of this, the final thing, the actual meat of the work that we do as part of data-oriented design is organize. Right, we have all, we know all the stuff, like, and all it's iterative, right? All the knowledge changes over time. Even what's most common can change over time. What's second most common, all, you know, so what the ranges and the user types, like all this can change over time, but we have to know it. And once we know it, we can start to organize it. And then, you know, if things change, we know we need to change it. So if we look at ECS in particular, it's a framework to help users organize at the end of the day. That's what it is. It's a, you know, it's a default organization strategy. It's a data closet. And you know, if every house has a built-in closet, every house is marginally more organized. If every house doesn't have closet, then by default, everyone solved that problem slightly differently, and more houses are dirty because there's just a bunch of stuff on the floor. Like that's the mental model here. Like we're providing a default organization strategy, so the default is organized or slightly more organized, more likely to be organized. And so there are plenty of performance gains to be got from just the most basic, most trivial organization strategy here. Massive performance. It turns out if you do any organization at all, you're going to see massive gains. That's, you know, I think probably obvious to most people. But it's also a runtime data protocol, right? So it's a way of a standardized way of systems to intercommunicate with each, you know, to communicate with each other. And those, in a nutshell, or a very, very large nutshell that we just took it, you know, now we're talking about, are the four elements of data-oriented design.
Right, thank you. That's a brilliant and kind of very mind-expanding overview of. There's a sort of, we see a lot of extra depth in that. Beyond that, and for anyone who's looked at it would know this as well. I think I know we're all time constraints. We've got another meeting to go to. I just wonder if are there any kind of questions for Mike before we sign off. I think everyone, we all need to jump to another meeting, but thank you very much for your time, Mike, and I really appreciate you sharing your insights of this, and yeah, it's very exciting stuff.
Yeah, thanks for having me.
Thank you. Bye.
All right. Bye.
Thank you.
Thanks a lot.